Emostel.
Hello, you are welcome to this video. In this tutorial, we're going to be talking about significant digits. Well, significant digits are digits that are important to your measurements or important to the calculation or to the numeric operation with your measurements. Okay, so significant digits are digits that their presence has an effect on your calculation, even despite the fact that it can even be zero, okay? But even despite being zero, it is significant. And that is the reason why I told you in the previous video and even in the video before the previous one, that in physics, if you write 1 in physics, it means something. If you write 1.0, it means something. This is zero that you are having here. There is a work that it is doing, and there is a message that it passes. So we don't carelessly write numbers in physics the way we could do in mathematics. Do you understand? So now we are going to see this importance in another dimension inside this topic that we are treating in this video. Right, but please take note of this. Number one is that all non-zero numbers are significant. All non-zero numbers, which means any number that is not zero. From 1, 2, 3, 4, 5, all non-zero numbers are significant. All right, take notes, that's number one. Well, number two about significant digits is that the number of zeros before before the number, like the number of zeros before, okay? And then the number of zeros after. The number of zeros before the number is not significant. The ones after are significant. I'm going to use this table to show you why they are not significant or why they are significant. You're going to see it yourself. But another way that we can look into significant digits is that significant digits are digits or numbers that have impact. They have impact on the relative error. They are numbers that have impact on the relative error. So, which means that because they can affect the relative error of a measurement, we see that, oh, they are very important, they are significant, because they have an effect on the relative error. So you know in physics, anything that has to do with error, we don't joke with it, okay? We are doing all of these topics because we are learning how to handle error in physics measurements when you are in the lab. We are taking measurements in the lab. Okay, you are just learning all of these things to know how to manage error in measurements and how to calculate, how to do calculations with them in such a way that the final result you get will still be a result that is accurate enough to depict the essence of the experiment. Do you understand it now? So that you will not just do an experiment and then at the end of the day, the values that you end up getting become so useless because it is just full of errors. So we are just trying to teach you how to manage errors, okay, numerically. And that is the essence of all these things that you've been learning. Now, like I told you, a significant figure or a significant digits, okay, is that which affects the relative error. Okay, now let's see whether relative error is going to be affected with these ones and with these ones or not. If you take note of this, we have 0.5, okay? So the unit of measure here will be what? 0.1 because it has only one decimal place. And then, you know, okay? So, and not about just because it has only one decimal place, also because it represents the tiniest number of graduation on the measuring instrument. And the tiniest number of graduation will be 0.1. And hence, the reason why we could have this. Then if we have 0.05, the unit of measure will be 0.01. Okay, because the unit of measure, we have the same number of decimal places as, you know, as the measurement that is being represented. Okay, the unit of measure here too, we have what? Since it is 3 decimal places, you have 0.001. The unit of measure will also have 3 decimal. Okay, and then the unit of measure here, since it does not have any decimal, it shows that it is a whole number. So what the unit of the whole number is what? Is 1. So you have 1. It shows that it's a whole number. Unit is whole. Do you understand it now? So Now, here you have 5.0. So the unit of measurement here is what? Is 0.1. Okay? And then the unit of measure here is 0.01. Okay? And so that is how it goes. Every whole number we have a unit of measure of what? Of 1. Even though it is 25, 30, 300. As far as the whole number and it doesn't have a decimal point, regardless of the value it is, the unit of measure is taken to be 1. Okay? Because it is the actual 1, the actual point on the ruler or the measuring instrument that measured it. Do you get what I'm trying to say? So you can picture it from that angle. Now, we have this settled. The possible error is going to be half of the unit of measure. So we are going to have 0.05 here, 0.005 here, 0.0005, okay? And then we have 0.5 here, we have 0.05 here, and then we have 0.005 here. All right, just check it out. Now, at the end of the whole thing, we are going to find the relative error. So the relative error, okay, let me just add this one because of this. I just want to balance things out. 5.000. So this one will be 0.001, and then this one will be 0.0005. Okay, good. Now, if you look at it very well, you will see that this number and this number here, they have the same words. They have the same value of possible error, which is 0.0005. Okay, all right. They have the same precision. As a result, okay, the precision is the same, as you can see, the precision is the same, but then the relative error is going to be different. So let's check it out. So relative error here now is that we are going to calculate, the relative error is calculated as what? The possible error divided by the actual measurement. So the possible error divided by the actual measurement will be 0.05 divided by 0.5. So let's quickly run it. 0.05 divided by 0.5. Okay, yeah, we have what? 1. All right, 0.05. Then the next one, 0.005, okay, divided by 0.5, we have 0.01 here. Okay, based on this, divided by 0. Okay, I made a mistake. Divided by 0.05. Okay, so we have 0.1. And so similarly, we are going to be having 0.01 here. If you do if you follow the trend, do you get it now? And then 0.5 divided by 5, that's 0.5. 0.5 divided by 5. So we have 0.1. Just check it out. 0.5 divided by 5, we have 0.1. And then 0.05 divided by 5.0, although mathematically is what? 0.01. And then if you follow the trend, we're going to keep having like 0.001, 0.0001. Do you understand? Now, as you can see, looking at what we have here, 0. Please, I want to recheck something here. 0.05, okay, divided by 0.5, 0.1, okay? This is 0.1. I made a mistake. I knew it was supposed to be the same. And also all through for this one. This one is 0.1. Then if you check this one too, it's supposed to be the same. 0.0005, that's 0.005, then divided by 0.005, you still have the same 0.1. Please, I beg your pardon here. I knew it is going to be the same. It was supposed to be the same. Okay, that's why I had to recheck the calculation. Okay, so but from here downwards, we have all these ones are correct. Okay, so as you can see, let's verify that again. 0.005 0.05 divided by 5, you have 0.01, 0.005 divided by 5, you still have, you have 0.01. This one is correct like this. So, okay, so the only one I just have to adjust is this. Please, I beg your pardon for that. Now, check this out. If you take note of it, you will see that the relative error is not affected by all the zeros, all of these zeros like this, that came before 5. None of these zeros affected the relative error, which shows that they are non-significant. And that is the essence of the second rule I told you. The first rule I told you is that every non-zero number is significant. Okay? Now, I said zeros that come before a significant figure or a significant number like this 5. Okay? Zeros that come before it, I told you that they are non-significant. As you can see, they did not affect the relative error, so which shows that they are non-significant. All right? And then these other ones affected the relative error, which shows that they are significant. And that is the reason why in physics, 5 is different from 5.0, because every of the zeros you represent here means something. They pass a message. They are significant. They are doing something. They are communicating something to the reader of the experiment. Do you understand it now? Hence, they are significant, as you can see. Okay? So that is that as per that. So this lesson is just dedicated to showing you significance and the rule that determines the significance of digits and all of that and why they are like that. Okay? So in the next video, we want to do a little bit of mathematics with significance figures or significant digits of a measurement. All right? And so I'm going to see you there. Take care. Bye.